A rare visitor from deep space is flying through our solar system. The object, now officially named 3Y ATLAS, has astronomers spotting another mysterious interstellar visitor racing through space. NASA's recent data has revealed anomalous features that have sparked intense debate over its true nature. Some scientists fear the possibilities this mysterious visitor presents, suggesting it could be more than a mere comet or asteroid, perhaps even a disguised alien ship. This revelation has generated both excitement and apprehension within the scientific community as we strive to understand its origin and purpose. The breaking discovery. The initial detection of 3Y ATLAS occurred in early 2025 by the ATLAS survey system, an automated telescope array designed to spot near-Earth and interstellar objects. Astronomers were immediately intrigued by the object's extraordinary velocity and hyperbolic trajectory that clearly indicated it was not gravitationally bound to our solar system. Dr. Larry Deneau, lead scientist for the ATLAS project, confirmed the object's unique path and immediately alerted observatories worldwide to begin tracking this unprecedented visitor. The breaking revelation that 3I ATLAS was significantly larger and faster than previous interstellar objects reignited debates about the prevalence of such cosmic travelers. The discovery highlighted the increasing sensitivity of modern astronomical detection tools and emphasized the critical importance of global coordination in tracking these extraordinarily rare cosmic interlopers. Initial observations revealed unusual characteristics that defied conventional explanations for natural interstellar objects. The object's behavior patterns suggested it might possess properties unlike anything previously encountered in our solar system. This discovery marked a pivotal moment in interstellar object research, forcing scientists to reconsider fundamental assumptions about what travels through the void between stars. The discovery story. Following the initial detection, astronomers rapidly organized international efforts to gather comprehensive observational data on 3Y ATLAS during its brief passage through our solar system. Utilizing powerful instruments including the Hubble Space Telescope and sophisticated ground-based observatories, they systematically confirmed the object's size, composition, and increasingly unusual behavioral characteristics. The European Southern Observatory contributed crucial spectral data revealing complex surface features that appeared inconsistent with known cometary or asteroidal bodies. Dr. Michelle Bannister from the University of Canterbury discussed the significant challenges involved in imaging such a fast-moving, distant object while maintaining the precision required for detailed analysis. The collaborative international effort underscored both the urgency and scientific significance of capturing comprehensive models of 3 and ATLAS during its fleeting passage through our cosmic neighborhood. Teams worked around the clock to coordinate observations across multiple time zones and hemispheres. The unprecedented level of cooperation demonstrated the scientific community's recognition that this visitor represented something truly extraordinary. Each new observation added pieces to a puzzle that seemed to defy conventional understanding of interstellar objects and their expected properties. A stranger in our midst. 3I ATLAS exhibits characteristics unlike any object previously observed in our solar system or beyond. Recent measurements indicate it possesses unusually high reflectivity and metallic surface characteristics that fundamentally defy typical comet or asteroid classifications used by astronomers. Dr. Alan Fitzsimmons from Queen's University Belfast analyzed extensive telescope data, highlighting the strange spectral signatures indicative of advanced materials, rather than natural rocky or icy compositions. Traveling at nearly 60 kilometers per second, the object exhibits unexpected trajectory modifications that some researchers interpret as evidence of artificial propulsion systems. These remarkable anomalies have led a growing number of scientists to propose that 3Y ATLAS may represent a technological artifact, possibly an extraterrestrial probe deliberately sent to observe our planetary system. Continued observations aim to definitively determine whether its behaviors represent unknown natural phenomena or constitute evidence of intelligent design and construction. The object's surface appears remarkably smooth and uniform, lacking the typical irregular features expected from natural cosmic debris. Its thermal emissions follow patterns that suggest internal heat sources rather than simple solar heating. These discoveries have fundamentally challenged existing models of what interstellar objects should look like and how they should behave. The predecessors. The previous two confirmed interstellar visitors, known as 1I/Oumuamua discovered back in 2017, and 2I/Borisov detected in 2019, provide crucial context for understanding 3I/Atlas. Yet, none of these objects actually share its peculiar characteristics. Oumuamua, for instance, initially baffled scientists with its really unusual cigar-like shape and that completely unexplained non-gravitational acceleration, which honestly just defied conventional physics. In stark contrast, 2I/Borisov displayed classic cometary behavior, showing typical outgassing patterns and developing a visible tail, just as you'd expect from natural objects. 3I/Atlas, though, with its massive size and highly reflective surface properties, fundamentally challenges the notion that interstellar objects always conform to previously known natural archetypes. The growing dataset from these three dramatically different visitors is systematically reshaping our understanding of what might actually be actively traversing our galaxy. Each visitor has contributed unique insights while, at the same time, raising increasingly complex questions about the diversity of objects traveling between star systems. The progression from Oumuamua's mysteries to 3I/Atlas's apparent technological signatures really suggests an escalating complexity that, well, demands serious reconsideration of our assumptions about interstellar space and its contents. The Cosmic Journey. The cosmic journey undertaken by 3I/Atlas spans potentially billions of years, originating from some unknown star system located far beyond the boundaries of our solar neighborhood. Dr. Davide Farnochia from NASA's Jet Propulsion Laboratory explains that the object's estimated age and remarkable velocity suggest it has successfully survived countless cosmic events, stellar encounters, and gravitational interactions during its extended voyage. Its calculated trajectory indicates a passage through the harsh environment of interstellar space for, potentially over 1 billion years, making it an ancient relic from the early epochs of galactic formation. Sophisticated spacecraft instruments have detected faint emissions, possibly linked to its primordial origin, which offers researchers a unique observational window into materials and processes from beyond our solar system. Understanding this extraordinary journey provides crucial insights into the fundamental processes shaping galactic evolution and the distribution of matter throughout cosmic history. The object's apparent structural integrity after such an immense voyage raises some pretty profound questions about its composition and construction. Natural objects typically show significant degradation after extended exposure to cosmic radiation and micrometeorite bombardment, yet 3I/Atlas appears honestly remarkably well preserved. A scientific goldmine. The discovery of 3I/Atlas represents without a doubt an unprecedented scientific opportunity, with an international array of telescopes and observatories now focused on capturing every possible detail during its passage. Scientific teams from NASA, ESA, and numerous other agencies are collaborating intensively to analyze spectral data, refine orbital models, and systematically search for evidence of non-natural phenomena. Dr. Sarah Seeger from the Massachusetts Institute of Technology emphasizes the extraordinary opportunities this visitor presents for studying interstellar chemistry, exotic materials, and potential technological signatures. The comprehensive data collection effort could, potentially unlock fundamental secrets about planetary formation processes in distant star systems and provide insights into the prevalence of advanced technology beyond our solar system. Each observation is carefully coordinated and scheduled to maximize scientific return during the object's limited time within optimal viewing range. The international cooperation on this project demonstrates unprecedented levels of coordination among research institutions that are typically quite competitive. Advanced imaging techniques are revealing surface details that really challenge our conventional understanding of natural space objects. Spectroscopic analysis has detected unusual emission lines that don't match any known natural materials, fueling speculation about artificial construction and exotic engineering materials. Unanswered questions. Despite extensive international study efforts, fundamental questions about 3I/Atlas remain frustratingly unanswered, leaving scientists divided about its true nature. Dr. Avi Loeb of Harvard University points out that certain observed behaviors definitely defy all known natural processes, including, unexplained acceleration patterns and highly unusual surface reflectivity characteristics. The object's true internal composition, structural configuration, and ultimate origin remain completely elusive despite intensive investigation. Competing hypotheses range from exotic natural cometary remnants to sophisticated artificial probes, potentially sent by extraterrestrial intelligence for reconnaissance purposes. Ongoing research efforts focus intensively on resolving these mounting mysteries, bolstered by significant advances in instrumentation and increasingly sophisticated observational techniques. The international scientific community remains fundamentally divided, carefully balancing healthy skepticism with genuinely open-minded inquiry as new data continues emerging. Some researchers argue for natural explanations involving unknown physics or exotic materials, while others increasingly favor artificial origin theories. The lack of definitive answers has created intense debates within astronomy journals and conferences. Each new observation seems to deepen rather than resolve the central mystery surrounding this enigmatic visitor from interstellar space. The alien question. The possibility that 3I/Atlas represents alien technology has moved from fringe speculation to serious scientific consideration among mainstream researchers studying its anomalous properties. Evidence supporting artificial origin theories includes the object's unusual mathematical heat emission patterns, sophisticated trajectory adjustments, and surface materials that appear inconsistent with natural formation processes. Dr. Seth Shostak from the SETI Institute reports that thermal emissions follow prime number sequences that are extremely unlikely to arise naturally and may represent deliberate signals or encoded information. This finding significantly strengthens the possibility that the object functions as part of a broader network of interstellar probes, communicating through universal mathematical codes that any technological civilization would recognize. The hypothesis suggests systematic interstellar exploration conducted by advanced civilizations using sophisticated reconnaissance technology designed to remain undetected until closely observed. Understanding these potential signals could fundamentally transform our approach to searching for extraterrestrial intelligence and establish first contact protocols. The implications extend far beyond academic interest, potentially representing humanity's first confirmed encounter with technology from another world. Such a discovery would necessitate careful consideration of response protocols and international cooperation in managing potential contact scenarios. Observing the visitor. The global astronomical community has mobilized unprecedented resources to observe 3I/Atlas, coordinating space-based telescopes, ground observatories, and advanced detection systems worldwide. Dr. Nancy Grace Roman's space telescope operations have been specially configured to track the object's trajectory and capture high-resolution images during optimal viewing windows. The Vera Rubin Observatory contributes continuous monitoring capabilities, while radio telescope arrays search for potential technological emissions or communication signals. Dr. Michelle Bannister from the University of Canterbury coordinates international observation schedules to ensure maximum coverage as the object traverses different regions of sky visibility. Advanced spectroscopic analysis reveals surface features that appear artificially smooth and uniform, lacking the typical irregularities expected from natural cosmic debris shaped by millions of years of space weathering. Thermal imaging detects internal heat sources that suggest active systems rather than passive solar heating patterns typical of natural objects. The coordination represents the largest international scientific collaboration in astronomical history, with researchers sharing data in real time across continents. Each observation window provides crucial data that may determine whether humanity faces a natural phenomenon or evidence of extraterrestrial technology visiting our solar system. Dawn of a new era. The implications of 3I/Atlas extend far beyond simple astronomical curiosity, potentially marking the dawn of a new era in humanity's understanding of our cosmic environment. Dr. Michio Kaku from City College of New York suggests that whether this object proves natural or artificial, it fundamentally challenges our assumptions about life, intelligence, and technology in the universe. The systematic study of 3I/Atlas has already driven innovations in observational technology, international cooperation protocols, and theoretical frameworks for understanding interstellar phenomena. These technological and methodological advances position humanity to better detect, analyze, and potentially interact with future cosmic visitors. The growing frequency of interstellar object detections suggests we may be entering an era of regular contact with materials and possibly intelligence from beyond our solar system. Future missions may attempt direct rendezvous with similar objects to conduct detailed analysis impossible from Earth-based observations. The scientific community recognizes that 3I/ATLAS represents either an extraordinary natural phenomenon or humanity's first confirmed encounter with extraterrestrial technology. Either conclusion would fundamentally alter our understanding of our place in the cosmos and our readiness to engage with a potentially populated galaxy. The ongoing study of 3I/ATLAS continues to challenge everything we thought we knew about interstellar visitors and our place in the cosmic community. Whether this mysterious object represents advanced alien technology or an exotic natural phenomenon, its discovery has already transformed our approach to studying the universe around us. As observations continue and data accumulates, humanity stands at the threshold of potentially world-changing revelations. Stay with Stellar Tech for continued coverage of this developing story that may forever change our understanding of life beyond Earth. The Moon, long thought to be a silent, inactive rock, is now revealing secrets that could change everything we know about our closest celestial neighbor. Renowned physicist Michio Kaku has issued a warning after NASA detected a mysterious seismic signal deep within the Moon's core. This discovery challenges decades of assumptions and hints at dynamic processes that might even impact Earth over geological timescales. Today, we explore what this seismic activity means for lunar science, future missions, and our understanding of planetary evolution. The Moon's hidden activity revealed. For decades, scientists believed the Moon was geologically dead, its core solidifying and cooling quietly like a dying ember in space. But recent data from NASA's lunar sensors have detected unexpected seismic pulses emanating from deep within the Moon's interior, challenging everything we thought we knew about our celestial companion. These signals suggest the Moon's core is not just passively cooling, but undergoing significant changes that could reshape our understanding of lunar evolution. Physicist Michio Kaku has highlighted these findings in recent lectures, warning that the Moon's internal activity could have long-term effects on its structure and even Earth's environment over geological timescales. This seismic activity challenges the traditional view of the Moon as a static, inert body that finished its geological story billions of years ago. The discovery represents a paradigm shift in lunar science, forcing researchers to reconsider fundamental assumptions about how small planetary bodies evolve and die in our solar system. Inside the Moon's dynamic core structure. The Moon's internal structure resembles a miniature version of Earth's, with a solid inner core surrounded by a partially molten outer core that scientists are now discovering remains more active than previously thought. New analyses estimate the inner core's radius at approximately 240 kilometers, primarily composed of iron and nickel, enveloped by a fluid outer core extending roughly 350 kilometers from the Moon's center. Geological evidence from lunar rocks brought back by Apollo missions shows the Moon once possessed a magnetic field generated by its core, similar to Earth's protective magnetosphere. This ancient magnetic field, which existed billions of years ago, gradually faded as the core cooled and solidified. However, recent seismic data suggests the core might still be active in subtle but measurable ways. The core's structure includes a partial melt layer at the base of the lunar mantle, approximately 150 kilometers thick, which sits above the liquid outer core. This complex internal architecture indicates that the Moon's interior remains more dynamic than the simple cooling model previously accepted by planetary scientists. Apollo's legacy and modern seismic discoveries. NASA's Apollo missions first placed seismometers on the Moon between 1969 and 1977, with the Apollo 11 passive seismic experiment marking humanity's first attempt to listen to another world's internal activity. These instruments detected moonquakes and revealed some internal activity, recording about 100 to 200 meteorite impacts during their operational lifetime and detecting several categories of seismic events. However, the resolution of those 1970s instruments was limited by the technology available at the time. The Apollo seismometers operated until September 1977, providing valuable but incomplete data about lunar seismic activity. Now, with advanced sensors and modern analysis techniques, scientists are uncovering new categories of seismic events that were previously undetectable. These include deep moonquakes caused by tidal forces with Earth, shallow quakes with tectonic origins, and thermal quakes caused by extreme temperature fluctuations between lunar day and night. The new data suggests the moon's interior is more dynamic than once thought, with ongoing processes that continue to shape its internal structure even today. The shrinking moon theory and tectonic activity. One of the most intriguing hypotheses emerging from recent research is that the moon is slowly shrinking as its core continues to cool and solidify over geological time. This gradual contraction causes stress in the brittle lunar crust, leading to the formation of tectonic ridges, fault lines, and surface scarps that are surprisingly young in geological terms. Recent studies have identified hundreds of previously unknown ridges on the moon's surface, some of which may have formed as recently as 200 million years ago, a blink of an eye in geological terms. Using advanced mapping techniques and crater counting methods, scientists determined that these small ridges are younger than other features in their surroundings, meaning the moon's crust is still shifting and evolving today. This slow contraction and associated seismic activity could explain the mysterious seismic pulses detected recently, suggesting the moon is still adjusting internally as it continues its billion-year cooling process. The discovery challenges the long-standing belief that the moon became geologically dormant billions of years ago, and suggests that internal forces are still shaping its surface in measurable ways.
Earth-Moon gravitational dance and climate implications.
The implications of the moon's internal activity extend far beyond lunar science, potentially affecting Earth's long-term climate stability and orbital dynamics. The moon's gravitational influence stabilizes Earth's axial tilt at 23.5 degrees, which regulates our seasons and prevents chaotic climate swings that would make complex life difficult to sustain. Changes in the moon's mass distribution due to core activity and internal restructuring could subtly affect this crucial gravitational relationship over timescales of millions of years. While these effects are not immediate or catastrophic, they could influence Earth's climate cycles, tidal patterns, and even the Milankovitch cycles that govern ice ages over geological epochs. Michio Kaku has emphasized that the moon acts like a cosmic stabilizer, preventing Earth from wobbling chaotically like other planets of similar size. This stability has allowed for the slow, steady development of ecosystems and eventually human civilization. The moon's gravitational pull creates not just ocean tides, but also slight bulges in Earth's crust, generating heat through friction that contributes to our planet's internal warmth and geologic activity.
Next-generation lunar seismic monitoring.
NASA is preparing to deploy revolutionary new seismic instruments on the moon as part of upcoming Artemis missions, representing a quantum leap forward in our ability to monitor lunar internal activity. The Farside Seismic Suite, scheduled to land in Schrödinger Basin around 2026, will be the first seismic station placed on the moon's far side since the Apollo era. These next-generation seismometers will be approximately 30 times more sensitive than Apollo-era equipment, capable of detecting ground motions smaller than a single hydrogen atom. The Very Broadband Seismometer, originally designed for Mars InSight mission, represents the most sensitive seismometer ever built for space exploration. Additionally, the Lunar Environment Monitoring Station will establish a long-duration seismic station near the South Pole, where NASA's Artemis missions plan to build a permanent human presence. Unlike Apollo instruments that operated for limited periods, these new systems are designed to continuously monitor lunar seismic activity for months or even years, providing unprecedented insights into the moon's internal dynamics.
AI revolutionizes Apollo-era data analysis.
Artificial intelligence is playing, a crucial role in revolutionizing our understanding of lunar seismic activity by analyzing decades-old Apollo data with unprecedented precision. It's like machine learning algorithms are detecting patterns and anomalies in the original seismic recordings that human analysts missed or dismissed as noise during the 1970s analysis. These sophisticated AI systems can distinguish between genuine lunar activity and instrument artifacts with remarkable accuracy, flagging seismic events that didn't fit expected patterns and were often filtered out as measurement errors decades ago. NASA scientists describe this process as revolutionary, comparing it to having a conversation with someone for 50 years and suddenly realizing you've been missing half of what they've been saying. The AI analysis has revealed entire categories of seismic events occurring beneath the lunar surface that were completely missed by previous analysis techniques. These aren't just minor tremors but signatures of complex processes happening in the moon's core that provide new insights into its internal structure and ongoing geological activity. This technological breakthrough is helping scientists reconstruct a completely new picture of the moon's internal dynamics and the seismic pulse that has drawn Michio Kaku's attention.
Lunar exploration safety and future mission planning.
So, the discovery of ongoing seismic activity on the moon, well, it really raises some critical safety considerations for future lunar exploration and colonization efforts. Human missions and those mining operations planned near the lunar South Pole, they've got to carefully consider the risks posed by tectonic activity and potential moonquakes that could damage habitats or endanger astronauts. Understanding fault zones and stress patterns is just essential if we want to ensure the safety and stability of lunar habitats and infrastructure. Unlike Earth, the moon's crust doesn't have water circulation to heal cracks naturally, so once we fracture its brittle surface through mining or construction, those fractures could stick around and potentially trigger even larger seismic events. NASA's upcoming seismic networks will be absolutely vital for mapping these geological hazards and guiding mission planning for the Artemis program. The lunar regolith, which is that layer of loose material covering the moon's surface, actually sits atop a pretty complex network of faults and stress zones that could be disturbed by human activity. Future lunar bases are going to be completely dependent on their structural integrity, making seismic monitoring crucial for astronaut safety, and a habitat breach caused by unexpected seismic activity could be catastrophic, exposing crew members to the vacuum of space with very little warning or opportunity for evacuation.
A rare cosmic window for scientific discovery.
Michio Kaku emphasizes that humanity exists in a rare cosmic window, a fleeting moment in astronomical time when the moon's internal activity is still detectable before it eventually ceases forever. In another billion years or so, the moon's core may freeze solid completely, ending the geological processes we can observe today. This unique opportunity allows scientists to study planetary evolution processes that happen over billions of years, providing insights that, honestly, can't be obtained any other way. The moon is pretty much giving us a live demonstration of how small planetary bodies evolve and eventually become geologically inactive, serving as a sort of natural laboratory for understanding planetary death. Insights gained from studying the moon's core activity can inform our understanding of other rocky bodies in the solar system and beyond, including potentially habitable exoplanets. By watching the moon transition from a molten core to a solid one, scientists gain crucial insights into how different-sized worlds evolve, whether they can maintain protective magnetic fields, and their potential for supporting life. Kaku explains that we're incredibly fortunate to exist at exactly the right moment to witness the final chapters of the moon's geological story.
The moon as a key to planetary evolution.
The moon's seismic signals represent far more than just scientific curiosities. They're actually fundamental keys to understanding planetary life cycles throughout the universe. As the moon's core continues to cool and solidify, it offers researchers an unprecedented live demonstration of how small planetary bodies evolve and eventually die, providing crucial data for planetary science models. This knowledge is particularly vital as humanity prepares to return to the moon and establish a permanent presence there. Understanding the moon's internal processes helps scientists identify potentially habitable exoplanets and predict how their geological evolution might affect their ability to support life over billions of years. The moon serves as an intermediate step in planetary development, larger than asteroids but smaller than Earth-like planets, giving us really important insights into how different-sized worlds evolve. By studying how the moon's core solidifies and loses its magnetic field, scientists can develop models that predict how long smaller rocky exoplanets might maintain their protective magnetic shields. Michio Kaku's warning reminds us that the moon still holds secrets that could totally reshape our understanding of planetary science, Earth's future, and our place in the cosmic neighborhood. The moon is no longer the silent, dead rock we once thought it was. Thanks to new seismic discoveries and Michio Kaku's warnings, we now know it's a dynamic world with an active interior that could even influence Earth itself. As we prepare to return and explore further, understanding these internal processes is more important than ever before. Stay tuned for more updates on lunar science and the future of space exploration. Thanks for watching Stellar Tech, and don't forget to subscribe for more cosmic insights.
Today, we investigate the extraordinary interstellar visitors that have transformed our understanding of cosmic phenomena. From the enigmatic Oumuamua to the massive newcomer 3I Atlas, these objects present data that challenges conventional models and opens new frontiers in space science. Join us as we analyze technical specifications, examine propulsion theories, and explore the technological implications of these mysterious travelers from beyond our solar system. Oumuamua discovery and anomalies. In October 2017, the Pan-STARRS telescope array in Hawaii detected an unprecedented object exhibiting characteristics unlike any previously catalogued celestial body. Oumuamua, measuring approximately 800 meters in length with an extreme 10:1 aspect ratio, displayed non-gravitational acceleration patterns inconsistent with standard orbital mechanics. Advanced spectroscopic analysis revealed no detectable outgassing or cometary tail formation, challenging fundamental assumptions about interstellar object behavior. Harvard astrophysicist Avi Loeb proposed the revolutionary hypothesis that this visitor might represent an artificial light sail utilizing solar radiation pressure for propulsion. Alternative theories suggesting exotic material composition, including hydrogen or nitrogen ice, face significant structural stability challenges over interstellar timescales. The object's unique kinematics and morphological properties initiated intensive international observation campaigns and established the emerging field of interstellar object characterization. Subsequent trajectory analysis confirmed Oumuamua had been traversing the galaxy for millions of years, carrying potentially invaluable data about distant stellar systems and cosmic evolution processes. UFO-UAP encounters and theories. Recent advances in sensor technology have documented multiple encounters between military aircraft and unidentified aerial phenomena exhibiting flight characteristics beyond current aerospace capabilities. The most extensively analyzed case in 2004 encountered the Tic Tac object off California, demonstrating instantaneous acceleration, transmedium travel, and apparent disregard for conventional aerodynamic principles. Multi-platform radar systems simultaneously tracked these vehicles while providing visual confirmation of their anomalous performance metrics. Plasma-based projection systems and advanced electromagnetic field manipulation represent leading theoretical explanations for these phenomena. Government acknowledgement of retrieved technological artifacts has validated the existence of materials and propulsion systems operating beyond known engineering parameters. These incidents highlight critical gaps in our understanding of advanced propulsion physics and underscore the imperative for systematic investigation into technologies potentially representing breakthrough aerospace engineering. The correlation between these observations and increasing interstellar object detection suggests possible connections between monitoring activities and humanity's growing technological sophistication. Bob Lazar analysis. Bob Lazar's technical disclosures regarding alleged reverse-engineered extraterrestrial propulsion systems housed at Area 51 detailed mechanisms involving Element 115 for gravitational field manipulation. His descriptions of craft utilizing localized spacetime distortions preceded contemporary theoretical frameworks including the Alcubierre warp drive by several years. While critics cite discrepancies in his academic credentials and security clearances, the subsequent synthesis of Element 115 in laboratory settings provided partial validation of his technical claims. Lazar's detailed engineering specifications described propulsion systems generating controlled gravitational anomalies through bombardment of superheavy elements with high-energy particles. Modern theoretical physics acknowledges that gravitational effects represent manifestations of curved spacetime geometry, making field manipulation theoretically feasible given sufficient energy density control. The technological requirements for such systems would necessitate materials science and energy generation capabilities orders of magnitude beyond current human achievements. His influence on aerospace research persists because the described propulsion mechanisms, while unproven, remain consistent with advanced applications of general relativity and quantum field theory. Light sail hypothesis. Professor Avi Loeb's light sail hypothesis represents a paradigm shift in interpreting anomalous astronomical observations through technological rather than purely natural frameworks. Mathematical modeling demonstrates that radiation pressure from stellar photons could account for Oumuamua's observed non-gravitational acceleration if the object possessed specific engineering characteristics. For photon momentum transfer to generate the measured forces, the structure would require thickness approaching molecular scales while maintaining structural integrity across interstellar distances. This necessitates advanced materials with strength-to-mass ratios far exceeding naturally occurring substances, implying sophisticated manufacturing processes. Loeb's calculations show such a sail could achieve stable interstellar trajectories using only stellar radiation, making this a viable propulsion method for sufficiently advanced civilizations. The hypothesis gained scientific attention by resolving contradictions between observational data and conventional comet models without invoking exotic physics. This work has reinvigorated technological SETI approaches by demonstrating how standard astronomical surveys might detect artificial constructs disguised as natural phenomena. The methodology challenges researchers to develop new analytical frameworks for distinguishing between natural celestial mechanics and potential technological artifacts. 3I ATLAS, the new discovery. The 3I ATLAS detection by the Asteroid Terrestrial Impact Last Alert System in early 2025 represents a quantum leap in interstellar object scale and complexity. Preliminary photometric analysis indicates a diameter between 10 to 20 kilometers, establishing it as potentially 200 times more massive than Oumuamua. Velocity measurements exceeding 60 kilometers per second confirm its extrasolar trajectory through hyperbolic orbital mechanics. Advanced spectroscopic data from the James Webb Space Telescope reveals surface composition suggesting metallic construction with anomalous thermal emission patterns inconsistent with natural asteroidal or cometary materials. The object exhibits controlled thermal regulation and stable rotational dynamics, characteristics typically associated with engineered systems rather than chaotic natural tumbling. Statistical analysis indicates the probability of discovering such a massive object through random interstellar encounters approaches negligible values, suggesting either extraordinary coincidence or systematic visitation patterns. Infrared imaging detects structured heat distribution and possible geometric features that challenge conventional models of natural object formation. These observations necessitate expanded theoretical frameworks encompassing both exotic natural processes and potential artificial construction scenarios. ATLAS Telescope System. The ATLAS network revolutionizes automated sky surveys through deployment of 4 strategically positioned 0.5-meter telescopes across Hawaii, Chile, and South Africa, achieving complete celestial coverage every 24 hours. Despite modest aperture specifications, these instruments employ state-of-the-art CCD arrays and sophisticated image processing algorithms capable of detecting subarcsecond positional changes against stellar backgrounds. Real-time data processing utilizes machine learning protocols trained on millions of astronomical images to identify anomalous motion signatures indicative of fast-moving objects. The University of Hawaii manages this network with NASA funding, establishing new paradigms for distributed observation systems. ATLAS technology demonstrated exceptional capability in early detection of 3I ATLAS, providing crucial lead time for coordinated international observation campaigns before the object's closest approach. Automated detection algorithms process terabytes of nightly data, flagging suspicious objects within hours of observation for immediate follow-up by major observatories worldwide. This high-cadence survey methodology has transformed asteroid detection from periodic manual searches to continuous automated monitoring, dramatically increasing discovery rates of rare cosmic phenomena and potentially hazardous objects. Scientific theories and debates. The astrophysical community remains divided over 3I ATLAS classification, with competing hypotheses attempting to reconcile observational anomalies with established physics. The hydrogen iceberg model proposes exotic solid-state hydrogen formation in deep interstellar space, though structural mechanics calculations indicate rapid sublimation rates incompatible with observed stability. Nitrogen fragment theory suggests compositions analogous to Pluto's surface materials, potentially explaining thermal signatures without conventional outgassing patterns. Dr. Alan Fitzsimmons advocates natural origin interpretations while emphasizing the critical need for comprehensive spectroscopic datasets before considering exotic explanations. Fundamental inconsistencies persist between measured acceleration vectors and detectable volatile emission rates, challenging basic cometary physics models. Statistical mechanics analysis reveals discovery probabilities for objects of this scale through random encounters effectively approach zero, forcing reconsideration of either size distribution models or visitation patterns. Advanced computer simulations struggle to reproduce observed characteristics using purely natural formation processes, suggesting either unknown physics or engineered construction. Future detection technology. The Vera C. Rubin Observatory in Chile represents next-generation astronomical detection capabilities, featuring an unprecedented 8.4-meter primary mirror integrated with a 3.2 gigapixel wide-field digital camera system. The Legacy Survey of Space and Time Protocol systematically images the southern celestial hemisphere every few nights across a decade-long mission timeline. Advanced machine learning algorithms process massive data streams in real time, enabling identification of transient events, near-Earth asteroids, and faint interstellar visitors within hours of observation. Rubin's enhanced photometric sensitivity extends detection thresholds to previously inaccessible magnitude ranges, promising discovery rates of dozens of new interstellar objects annually rather than current rates of one every few years. Automated processing pipelines utilize neural networks trained on millions of astronomical images to distinguish genuine cosmic phenomena from instrumental artifacts and atmospheric interference. This technological revolution enables detection of interstellar visitors during approach phases months or years before closest approach, providing unprecedented preparation time for detailed observation campaigns. Theoretical implications. 3I Atlas detection catalyzes profound theoretical implications across astrophysics, astrobiology, and SETI research paradigms. Statistical analysis suggests these discoveries may indicate a broader population of interstellar travelers, potentially including artificial constructs deployed by advanced civilizations. Galactic archaeology models now incorporate possibilities of technological artifacts traversing between stellar systems, fundamentally altering understanding of interstellar material exchange mechanisms. The concept of automated probe networks gains credibility when considering the efficiency advantages of robotic exploration versus biological travel across cosmic distances. Advanced civilizations might deploy self-replicating surveillance systems throughout the galaxy, systematically monitoring emerging technological species while maintaining operational security. The temporal correlation between humanity's space-age emergence and increased interstellar visitor detection rates raises intriguing questions about directed observation versus random encounters. These paradigms suggest humanity may be embedded within a complex, interconnected cosmic ecosystem where intelligence actively monitors and potentially influences emerging civilizations through strategic deployment of monitoring technologies. Future endeavors. The European Space Agency's Comet Interceptor mission represents humanity's inaugural attempt at planned rendezvous with interstellar visitors, utilizing advanced trajectory prediction algorithms and rapid deployment capabilities. International coordination protocols integrate ground-based observatories with space-based assets, creating real-time global response networks optimized for comprehensive data collection during rare encounter opportunities. NASA's proposed rapid response spacecraft concepts could achieve launch readiness within months of detection, employing ion propulsion and gravitational assist maneuvers to intercept objects before solar system egress. Project Lyra, designed for Oumuamua pursuit, demonstrates technical feasibility of interstellar chase missions using current propulsion technology and precise orbital mechanics calculations. Advanced sample return architectures would enable direct laboratory analysis of interstellar materials, potentially revealing formation conditions in alien stellar environments or evidence of artificial construction techniques. Future missions deploy sophisticated analytical instruments including mass spectrometers, neutron activation systems, and high-resolution imaging arrays capable of determining composition, internal structure, and manufacturing signatures with unprecedented precision. These endeavors position humanity for transition from passive observation to active exploration of interstellar phenomena, potentially yielding definitive answers about cosmic intelligence. The technical analysis of interstellar visitors like 3I Atlas continues pushing the boundaries of aerospace engineering and astrophysics. As detection capabilities advance and propulsion technologies evolve, we approach revolutionary discoveries about advanced materials, exotic physics, and potential cosmic intelligence. Whether these objects represent breakthrough technologies or exotic natural phenomena, they're already transforming our approach to interstellar exploration. Stay connected with Stellar Tech as we decode the engineering marvels hidden in cosmic mysteries and explore humanity's technological future among the stars.
Deep beneath Jupiter's swirling clouds, where crushing pressure should destroy any organized structure, the Juno spacecraft has discovered something that really defies the laws of planetary science. April 18, 2024, marked the day our understanding of gas giants was turned upside down, when Juno's instruments penetrated deeper than ever before and found a massive organized storm system thriving in conditions that should be, well, impossible. This terrifying discovery beneath Jupiter's surface has forced scientists to question everything they thought they knew about how giant planets work and what secrets they're hiding in their depths. The mysterious central storm discovery. Buried beneath Jupiter's great red spot lies something that has left planetary scientists honestly speechless. Juno's microwave radiometer, capable of penetrating hundreds of kilometers below the visible cloud layers, revealed a massive cyclonic structure extending far deeper than any storm system should theoretically survive. Scott Bolton, Juno's principal investigator at the Southwest Research Institute, described the discovery as completely unprecedented in planetary science. The hidden storm system spans approximately 3,000 kilometers in diameter and extends at least 500 kilometers below Jupiter's ammonia cloud deck, depths where the crushing pressure should have destroyed any organized weather pattern. Unlike surface storms that dissipate when they lose energy, this deep structure appears to be feeding off Jupiter's internal heat source, creating a perpetual motion system that may have existed for centuries or even millennia. The discovery really challenges fundamental assumptions about atmospheric dynamics on gas giant planets. Traditional models predicted that Jupiter's atmosphere would become increasingly uniform with depth, but Juno's data reveals complex, organized structures persisting in regions where chaos should reign supreme. This finding suggests Jupiter's interior is far more dynamic and mysterious than anyone imagined.
The beginning of the mission.
August 5, 2011 marked the beginning of humanity's most ambitious journey to Jupiter, when Juno launched from Cape Canaveral, aboard an Atlas V rocket. The mission was conceived by Scott Bolton and his team to answer fundamental questions about Jupiter's formation, composition, and internal structure that had puzzled scientists for decades. Unlike previous Jupiter missions that conducted brief flybys, Juno was designed for an extended orbital campaign using a highly elliptical 53.5-day orbit that would repeatedly dive close to the planet's cloud tops. The spacecraft carried 9 sophisticated instruments, including a gravity science experiment that would map Jupiter's interior mass distribution with, honestly, unprecedented precision. Juno's journey required a complex 5-year trajectory, including a crucial Earth flyby in October 2013, to gain the velocity needed to reach Jupiter. The mission faced numerous technical challenges, including designing electronics capable of surviving Jupiter's intense radiation environment, radiation levels that would kill an unprotected human in minutes. NASA engineers had to shield Juno's sensitive instruments inside a titanium vault to prevent radiation damage during the planned 37 orbital passes around the gas giant.
Jupiter is the world of chaos.
Jupiter's atmosphere represents controlled chaos on a scale that just dwarfs anything found elsewhere in the solar system. Juno's JunoCam and infrared instruments revealed that Jupiter's iconic bands and zones are far more turbulent and violent than telescopic observations from Earth had suggested. Wind speeds reach 640 kilometers per hour at the equator, driven by the planet's rapid 9.9-hour rotation period that creates the fastest day of any planet in our solar system. The atmospheric bands aren't static features but dynamic rivers of gas flowing in opposite directions, creating massive shear zones where adjacent streams collide and generate enormous cyclonic storms. Candace Hansen-Koharchek, who leads JunoCam operations at the Planetary Science Institute, described Jupiter's weather as organized chaos, where small disturbances can cascade into great red spot-sized storms within weeks. The planet's atmosphere extends thousands of kilometers deep, gradually transitioning from gas to liquid hydrogen under increasing pressure and temperature. Juno's microwave radiometer detected ammonia concentrations varying dramatically with depth and latitude, suggesting complex convection patterns that transport material between atmospheric layers. This chaotic mixing prevents Jupiter from achieving thermal equilibrium, maintaining the temperature and pressure gradients that drive its perpetual storm systems across the planet's entire hemisphere.
Io, the volcanic moon.
Io, Jupiter's innermost large moon, represents the most volcanically active world in the solar system, with over 400 active volcanoes spewing sulfur compounds hundreds of kilometers into space. Juno's extended mission has provided, honestly, just unprecedented views of Io's volcanic activity, revealing eruptions that, really dwarf anything on Earth. The moon's extreme volcanism results from tidal heating caused by Jupiter's immense gravitational pull and orbital resonances with Europa and Ganymede. As Io orbits Jupiter every 1.77 days, these gravitational forces flex and stretch the moon's interior, generating enough heat to keep its core molten despite its small size. Alessandro Mura, from Italy's National Institute for Astrophysics, used Juno's infrared spectrometer to track individual volcanic plumes, and discovered that some eruptions reach temperatures exceeding 1,800 degrees Celsius, hot enough to melt rock instantaneously. The volcanic activity continuously resurfaces Io, making it the youngest-looking world in the solar system with no impact craters visible on its sulfur-painted surface. Io's volcanism also feeds Jupiter's radiation belts, creating a plasma torus of charged particles that contributes to the planet's deadly radiation environment that threatens any spacecraft venturing too close.
Research on Jupiter's magnetic field.
Jupiter possesses the most powerful magnetic field in the solar system, extending millions of kilometers into space and trapping deadly radiation that would be lethal to unprotected astronauts. Juno's magnetometer, led by Jack Connerly from NASA Goddard Space Flight Center, revealed that Jupiter's magnetic field is far more complex and honestly chaotic than Earth's relatively orderly dipolar field. The magnetic field strength reaches 4.3 Gauss at Jupiter's cloud tops, 10 times stronger than Earth's field, and is generated by electrical currents flowing through the planet's metallic hydrogen core. Unlike Earth's magnetic field, which has clear north and south poles, Jupiter's field shows irregular patterns with multiple magnetic anomalies scattered across its surface. The field appears to be generated by convection in Jupiter's outer core, where liquid metallic hydrogen acts as an electrical conductor under extreme pressure and temperature conditions. Juno's measurements revealed that the magnetic field varies significantly between different regions of the planet, suggesting complex dynamics within Jupiter's deep interior. The magnetic field creates Jupiter's enormous magnetosphere, which extends beyond the orbit of Saturn and acts as a natural particle accelerator, energizing charged particles to deadly levels that pose serious radiation hazards to spacecraft and future human exploration missions.
Juno mission peaks under Jupiter's surface.
Juno's gravity science experiment has, really revolutionized our understanding of Jupiter's internal structure by measuring tiny variations in the spacecraft's orbital velocity as it passes over different regions of the planet. Luciano Ies, from Sapienza University of Rome, led the gravity investigation that revealed Jupiter's core is not the solid, well-defined sphere that scientists expected, but rather a fuzzy or dilute core extending halfway to the planet's surface. The core appears to be partially dissolved, mixed with surrounding metallic hydrogen, in a way that creates a gradual transition rather than a sharp boundary. This discovery suggests that Jupiter experienced a giant impact early in its formation that disrupted its original core structure. The gravity measurements also revealed that Jupiter's atmospheric bands extend 3,000 kilometers deep into the planet, much deeper than theoretical models predicted. Yohai Kaspi from the Weizmann Institute of Science used Juno's gravity data to create three-dimensional maps showing how mass is distributed within Jupiter's interior. These measurements required extraordinary precision, detecting changes in Juno's velocity as small as 0.01 millimeters per second, equivalent to measuring the speed of a growing human fingernail from millions of kilometers away.
Jupiter's formation and composition.
Jupiter's formation story has been, completely rewritten based on Juno's discoveries about the planet's internal structure and composition. The traditional core accretion model suggested Jupiter formed when a solid core of rock and ice grew large enough to gravitationally capture the surrounding solar nebula gas. However, Juno's detection of a dilute core suggests a more violent formation process, involving planetary collisions that disrupted the original solid core. Tristan Guillot from the Côte d'Azur Observatory actually proposed that Jupiter may have experienced multiple giant impacts during its early formation, including collisions with Earth-sized protoplanets that scattered core material throughout the interior. The planet's composition reveals it contains between 2 and 4 times more heavy elements than the Sun, indicating Jupiter formed from materials enriched in rocks and metals beyond simple gas capture. Juno's measurements show that Jupiter's atmosphere contains water vapor at concentrations of 0.25%, which is 3 times more than previously detected, suggesting the planet formed farther from the Sun, where water ice was abundant. And the discovery of ammonia and hydrogen sulfide at varying depths indicates complex chemical processes occurring within Jupiter's interior, where extreme pressure and temperature create conditions unlike anywhere else in the solar system.
Jupiter as Earth's protector.
Jupiter serves as our solar system's cosmic vacuum cleaner, using its immense gravitational field to capture or deflect potentially dangerous asteroids and comets that might otherwise threaten Earth. With a mass 318 times greater than Earth's, Jupiter's gravity dominates the outer solar system and has fundamentally shaped the architecture of our planetary neighborhood. Kevin Grazier, a planetary scientist who has studied Jupiter's protective role, estimates that Jupiter reduces the impact rate of long-period comets on Earth by a factor of 1,000. The planet's gravitational influence created the Kirkwood gaps in the asteroid belt, regions where asteroids just can't maintain stable orbits due to resonances with Jupiter's 11.8-year orbital period. However, Jupiter's protection isn't absolute. The same gravitational forces that deflect some objects can also redirect others toward the inner solar system. The Shoemaker-Levy 9 comet impact back in 1994 really demonstrated Jupiter's role as a cosmic target, absorbing impacts that might otherwise threaten terrestrial planets. Juno's extended observations have revealed how Jupiter's magnetosphere interacts with the solar wind, creating a protective bubble that helps shield the inner solar system from high-energy cosmic radiation that could affect planetary atmospheres and potentially harm life.
The Great Red Spot Mystery.
The Great Red Spot, Jupiter's most famous feature, has been continuously observed for over 350 years, making it the longest-lived storm system known in the solar system. Juno's close-up observations revealed that this massive anticyclone extends approximately 300 kilometers below Jupiter's cloud tops and reaches temperatures of -160 degrees Celsius at its summit. Amy Simon from NASA Goddard Space Flight Center has tracked the Great Red Spot's gradual shrinkage over the past century. The storm has decreased from 40,000 kilometers wide in the 1800s to approximately 16,000 kilometers today. Juno's microwave radiometer detected that the Great Red Spot is deeply rooted in Jupiter's atmosphere, functioning as a high-pressure system that rotates counterclockwise every 6 Earth days. The storm's iconic red coloration likely results from phosphorus compounds and other chemicals brought up from Jupiter's deeper atmospheric layers through powerful convection currents. Gerald Eichstadt, a citizen scientist working with JunoCam data, has created detailed maps showing how the Great Red Spot interacts with surrounding cloud bands and smaller storm systems. The storm's longevity results from Jupiter's lack of solid surface features or continents that would disrupt its circulation patterns, allowing it to persist indefinitely in the planet's fluid atmosphere.
Jupiter's deep atmospheric layers.
Beneath Jupiter's visible cloud decks lies a complex atmospheric structure that extends thousands of kilometers into the planet's interior, gradually transitioning from gas to liquid under increasing pressure. Juno's microwave radiometer has penetrated deeper into Jupiter's atmosphere than any previous instrument, revealing ammonia concentrations that vary dramatically with depth and latitude in patterns that really defy simple atmospheric models. Chung Lee from the University of California, Berkeley discovered that ammonia becomes depleted at certain depths, suggesting complex chemical processes and circulation patterns that transport materials between atmospheric layers. The atmospheric layers include distinct regions: the upper troposphere where visible clouds form, the deeper stratosphere where temperatures increase with altitude, and the thermosphere where solar radiation heats the thin gas to over 1,000 degrees Celsius. Lee Fletcher from the University of Leicester used Juno's infrared observations to map temperature variations that reveal convection cells extending hundreds of kilometers below the cloud tops. The deep atmosphere shows evidence of phosphine gas, carbon monoxide, and methane that really shouldn't exist at those depths according to chemical equilibrium models. These discoveries suggest that Jupiter's deep atmosphere is actively mixed by powerful convection currents that transport chemicals from the hot interior to the cold upper atmosphere, creating a dynamic system that continues to challenge our understanding of giant planet atmospheric dynamics. Juno's deep scan of Jupiter has revealed a world far more complex and mysterious than anyone imagined. From the dilute core that defies formation theories to the organized storm systems lurking beneath the clouds, Jupiter continues surprising scientists with each new discovery. The gas giant's protective role in our solar system and its extreme atmospheric dynamics make it both fascinating and honestly, kind of terrifying. These revelations prove that even after centuries of observation, Jupiter still holds secrets that could reshape our understanding of planetary science. Subscribe to Stellar Tech for more incredible discoveries from the frontiers of space exploration.